So, we continue with our discussion on application of heat transfer, and yesterday I had introduced two different problems. One is cooling of a slab or an ingot, and the other is the reverse of it, that is the heating of an ingot or a slab. And in that context, I have provided a process description, because without knowing the process, you really cannot understand that what are the intricacies, or how to formulate the equations, how to solve the equations, what are the applicable boundary conditions, and so on and so forth. Now, before I move on to the next, I would like you to note that, for example, if you say furnace cooling versus air cooling, as it is done in the case of normal air cooling, if you try to distinguish these two processes, as it is in the case of annealing and normalizing operations, which you normally encounter or frequently encounter in metals processing. So, the furnace cooling and normal air cooling, they are essentially one and the same process. But if you have to, for example, write down the equations and the boundary conditions, can you visualize that where, through which terms or through which expressions the two processes are going to be distinguished. For example, you should be able to visualize it by now, because the furnace cooling essentially implies that normal air cooling, what happens is, if you look at the normal air cooling graph. So, suppose you have a time versus temperature, and this is your ambient temperature. Okay? This is T A, and that is how the average temperature of the solid will change as a function of time. Okay? And this is what is this graph? This graph is about T average, and this is a volumetric average of the temperature. So, I think T average basically is 1 by V, okay? And then we have integral T x y z. That is what it is. So, you have to numerically integrate after you know the temperature. So, you should be able to find out a volumetric average temperature, and so it is a function, T is a function of time and the spatial locations. Now, you are averaging it, and so you are having only this is, I would say, this is T average and this is T average. So, that's a characteristic kind of a plot. Now, in the case of furnace cooling operation, because the object is kept in the furnace itself, so now again the solid average temperature is going to be decreasing as a function of time. Okay. So, but you must understand, this is our T is equal to 0, and this is maybe 25 degrees centigrade, okay. And this is the time at which the ingot is stripped, or the slab is ready or it is cast, and that is the time T is equal to 0, from which how the temperature changes. Now, if the ingot would have been in the furnace, and I say that this is again T is equal to 0. So, at time T is equal to 0, so the furnace, okay, the ingot and the furnace temperature, if we assume that they have reached a steady state, there is a thermal equilibrium between the two. So, both of this will start at the same temperature, and that temperature is going to decrease. Okay. And similarly, the furnace temperature will also decrease, and the furnace temperature possibly will decrease, because I have shut down the energy, and as a result of which, and ultimately at very long time, both the furnace and the solid. So, this is the solid temperature and this is the furnace temperature. That is how the temperature is going to. So, therefore, if you want to simulate the process, although the governing equations, if you say there is the same ingot, okay, same material, same size, everything remains the same, you want to perform a furnace cooling, you want to formulate the equations etc. for furnace cooling vis-a-vis the normal air cooling. So, you can see here that the ambient temperature, which dictates my boundary condition, while this remains constant as a function of time in the air cooling process, the ambient temperature in the case of furnace cooling, okay, is This is the furnace temperature. So, the ingot is within the furnace itself. So, the ambient is no more 25 degrees centigrade, but the ambient is the within the furnace temperature, and that furnace temperature is changing as a function of time. So, this essentially is the difference between the two processes. So, the rate of cooling is going to be substantially smaller in the case of, so that is why I have drawn this line a little bit steeper than this particular line to show that indeed in air cooling I would expect that the graph would be, cooling rates would be higher. So, in this particular case what is going to happen, because the ambient temperature dictates my boundary condition. So, therefore, the furnace temperature in this case, which is related to the boundary condition, is going to be different. So, everything is going to be same as far as the two formulation of the two processes are concerned, except that the surface boundary conditions are going to be identical. In one case, the surface boundary condition, if you formulate it in terms of exclusive radiation rate law, then the furnace, the ambient temperature 25 degrees, a constant ambient temperature can be taken to formulate the surface boundary condition. On the other hand, in this particular process, what happens? A time dependent furnace temperature has to be taken as the ambient temperature. So, therefore, theta A in this case is constant, and in this case theta A, which is equal to theta F CE furnace, and this is actually a function of T, and this history is to be given to us in order to formulate the boundary condition. We cannot say that we do not know this, okay, then the boundary condition, because the boundary condition will have theta surface to the power 4 minus theta ambient to the power 4. Theta surface to the power 4 is already an unknown parameter, because that I do not know, it is changing as a function of time. I want to find it out, and in this particular case what happens is, so the ambient temperature itself must be provided, otherwise you have one additional unknown and you cannot solve this problem. So, a furnace step cooling operation as far as the heat transfer fundamental goes, okay, we understand that a furnace, now let us look at it from a mathematical point of view, or from the heat transfer fundamentals point of view, that a furnace cooling, when you read metallurgical literature, we say that a furnace cooling means that it is cooling at a lesser rate than it is normal air cooling, and we understand it fundamentally that why it is cooling at a lesser rate, because the ambient temperature is 6 in which the ingot is subjected during furnace cooling operation is at a substantially higher temperature and is changing as a function of time. It is only at very large time that this temperature may acquire a temperature of the global ambient temperature, which is the room temperature itself, but otherwise within the process duration for T is equal to greater than 0 to some time, the ambient temperature is always higher. So, the differential temperature between the ingot surface and the ambient temperature is always small in the case of furnace cooling than it is in the case of air cooling. So, the driving force for heat transfer from the ingot to the surrounding is lower here, the driving force for heat transfer from the ingot to the surrounding is higher here, as a result of which the cooling rates is smaller here and the cooling rate is larger here. That is the essential difference between the furnace cooling as well as air cooling operation. Now, let us go into, with this I think I have talked enough about the cooling and heating operations of ingots and slabs. Let us talk of another class of problem, which is the heat treatment operation. Basically, I want to quenching. Sometimes you can say air cooling, forced air cooling. If you have forced air cooling, in that case, forced air cooling essentially will mean, suppose if I say that I want to do this, normal air cooling, but I want to do it a forced air cooling. So, in that case, my boundary condition is going to be whatever is the boundary condition here, plus we will have a convective heat transfer component, that is H into T surface minus T ambient, and that heat transfer coefficient is going to be large because of the fact that we are using a forced convective heat transfer condition, we are blowing some kind of an air or so on and so forth. So, same methodology applies in the case of forced air cooling. When you have quenching, for example, I would say the heat transfer coefficient is even larger, and in the case of quenching, what happens particularly when you put in solid object into a liquid bath which is at room temperature, okay, we have a boiling heat transfer, and the boiling heat transfer coefficients are substantially larger okay, and that is a complete different subject altogether. That on the surface of the solid, what happens the moment the solid gets into the water, is plunged into the water or into a liquid, what happens is because the water has low boiling point, so 100 degrees centigrade or so. So what is happening, if you put a steel ingot or an aluminum ingot which is having 700 or 900 degrees centigrade, the water starts on contact with the solid, will start to boil immediately, okay, and as a result of which air films are going to form. This is a separate subject of which you call as a boiling heat transfer. Okay, that sort of a condition is going to be prevalent, and we have to have a heat transfer coefficient. So we have to express a boundary condition in terms of the boiling heat transfer coefficient, and that needs to be also taken into account. Now, as far as you may have come across during your physical metallurgy courses, wire rod cooling to have fine pyrolytic structure in steel rods. So the steel rods are often subjected to air cooling, and if you do, if the size of the wire is such that if you use a very severe cooling rate, then what happens is there is a possibility that you may go into the nose of the TTT diagram. That I think you all know about the time transformation. So you have taught about this, that and these are the C curves, and we know that this is the critical cooling rate which gives us the martensitic structure. But even if you have a cooling rate which is like this, we can have a Benedict structure or something like that. This I think you all know, so I don't have to dwell on this to a great detail. But wire rod cooling, to strengthen the properties of because the grain size is related to the material property, performance and the property. So the grain size, finer grain size gives us, in a layman's term, better toughness or better strength, and the coarser grain size gives us, as you all know, relatively poorer strength. And the grain size is going to be dependent on the rate of cooling, for example. Okay, so as a result of air cooling of rods, basically what happens is that we take the rod at a high temperature and then cool it quite rapidly, not just normal air cooling, forced air cooling, okay, or maybe air mist cooling, and as a result of which what happens is we intend to form the pyrolytic structure, fine pyrolytic structure, which gives us better mechanical properties. In some cases also, we would like to, when you quench, we want to form martensite, and then we want to do tempering, as in the case of steel, in order to get better mechanical properties. So what happens is we want to find out sometimes that whether retained austenite is there or not. Retained austenite, as you all know, is a very detrimental material as far as the mechanical properties is concerned. So the rate of cooling, this time temperature graph, this is the time temperature graph you see that I have drawn in the case of furnace cooling as well as in the case of furnace cooling and air cooling. And whatever I have drawn here, these dotted lines, these are also time temperature graphs, these are cooling curves. So if you know the cooling curves, in that case from the cooling curves, by taking the corresponding the time temperature transformation diagram, we should be able to find out that what is the possibility of formation of martensite or fine pyrolytic structure. If the cooling rate goes something like this, there's a fine pyrolytic structure is going to be, this is the structure. Okay, this is an intermediate structure, this is a pure martensitic structure. Okay, this is an intermediate structure containing benite, etc. And this graph, if the cooling graph is like this, in that case the fine pyrolytic structure is going to result. So wire cooling, if you consider the wire cooling operation, in that case what happens is the wires are basically long, so you can approximate as an infinite cylinder. So you can only look at the cross section of the wire that what is really happening. So that there's a theta symmetry which exists, because it's a complete round wire, and also the wire is very long, so an infinitely long cylindrical cylinder concept holds good, and therefore you can study the heat transfer related issues by considering only the radial conduction of heat. Okay, and therefore if you take the cross section of the wire like this, okay, and of course this wire may be sometimes moving also. Okay, so therefore there may be, you may have an unsteady state heat conduction, and you may have what you call a component along the z direction, which is, suppose if you imagine you have a wire like this, okay, and this wire has a cross sectional area like this. So, if you take any cross section here, okay, the volume element and perform energy balance. So, this is what it is basically. That is a cylindrical portion of this. So, this is the delta z. So, if the control volume is fixed in space, you can imagine that if the wire is moving, in that case there will be a net axial conduction term. This represents my z direction and this represents my r direction. The problem needs to be discussed with theta direction, because it is an actually symmetrical about theta. So, in this particular case what happens is that heat is transported in the radial direction, because you have over it air which is flowing, forced air cooling. So, heat is being extracted in the radial direction. So, there is a gradient. Temperature is a function of r, and temperature is going to be a function of z also, because the simple fact that heat is going to be flowing because of the motion of the wire itself. On the other hand, if we consider, so the process is unsteady in nature, it is not going to be a steady process, okay, and therefore, you can consider there are two possibilities, that the radial heat transfer can be taken for a stagnant wire, okay, or the radial heat transfer can be taken for a moving wire. If you take a moving wire, in that case just an axial conduction term has to be added, and that can be derived very easily by taking an elemental cylindrical control volume. So, let us consider for the time being that, so this could be as a function of z also, and this could be as a function of t also, okay, but we do not want to consider this. We can consider that there is, the cylinder is infinitely long, it is stationary, there is only radial heat transfer. So, we consider this, and if we write down the equation, therefore, then we have that is basically that represents the radial direction heat conduction equation. This describes the variation of temperature as a function of radial coordinate and as a function of time itself. And what does this q dash triple prime indicate? It indicates a volumetric source heat source term, and that volumetric heat source term in this particular case could be something like rho, density of steel, multiplied by the heat of formation, and this is the rate of phase change as a function. So, this is the phase transformed, volume fraction transformed, rate of change of volume fractions, okay, of the new phases that is being generated. This is the heat of transformation for the reaction, solid state reaction which is taking place, maybe from austenite to perlite. Okay. So, at t is equal to 0, the wire may be heated in a furnace, okay. It is at a homogeneous temperature. So, we know that the heating problem we have studied, and now the wire is brought out, and what happens is over it a strong convection current of air is being passed, or the wire may be quenched also, does not matter, it will only change the boundary conditions, and then we want to find out. So, there are the variation of temperature within the wire as a function of time, and as the homogeneous piece of wire is brought out and it is subject to forced air cooling, then what happens is there are solid state phase transformation reactions which start, and austenite will, as the temperature goes down below the AC3 temperature, what happens, that austenite will get transferred into perlite, and this basically, so there is a change in the volume fraction, okay, from austenite to ferrite. How much of austenite is there, and how much of there is going to be either austenite or perlite, and when the transformation is going to be completed, it is going to be 100% perlite. So there is a rate of change of phase transformation here, okay, or the new phase forming here, and this represents the enthalpy of the reaction, and which is in terms of joules per kg, and rho is equal to kg per meter cube. So what we get here, this is volume, this is dimensionless, this is volume fraction, this is time, and this is joules per kg, and this is kg per meter cube. So what you get, joules per second per meter cube, that is what it is, or watt per meter cube, and you know that the source term, all the terms in the governing equations have a dimension of watt per meter cube, this term, and this term as well. So this can be formulated. Now the question is, how do you know this, how the phase change is taking place? For example, you can club with an iron carbon phase diagram, assuming that you are doing air cooling, and you know that the thickness is so small, nowhere you will get critical cooling rate. So the time transformation diagram does not come into the picture. You can assume that the phase change is occurring close to equilibrium, and therefore you can apply the iron carbon phase diagram, and you can apply Lever rule, and you can find out at any point of time how much of austenite is being converted to how much of perlite. So this term can be calculated, but this itself is going to be a function of temperature itself, because in the equilibrium diagram, what do you get? You can get the volume fractions provided at a certain temperature only. There is no concept of any time. Okay, the time comes from your that you want to find out at a certain amount of time. So this is a parameter that you say that I know the field, I know the distribution at time t is equal to 0. I want to find out that at 2 seconds after this time 0, what happens, and then this time basically becomes the 2 seconds, and in that 2 seconds of time you are predicting the change in temperature, and that change in temperature will precipitate into a change in the phase volume fraction. So this term can be very conveniently calculated, but this term brings in non-linearity into the equation, because this is not known, this is only known only when the temperature is can be calculated. Now in order to, so the source term can be formulated, so as I have indicated here, and we have, for this particular equation, we have an initial condition, and we have two boundary conditions for the second order equation. Okay, and this is for all values of R, and if I have homogenized the wire already in a big furnace, okay, in a tube furnace or something like that, in that case I can say that everywhere the temperature at all R for T is equal to 0, which I have already stated is equal to T0, which is the homogenization temperature. So I have taken the entire wire to its AC3 or temperature, which is greater than the AC3, maybe 1180 or 1200 degrees centigrade or so. Anything greater than, I think, 930 degrees centigrade should suffice. So it is a homogeneous temperature, and that is the initial condition. At time t is equal to greater than 0. So we have at R is equal to 0, because of the radial symmetry, we have the flux condition is equal to 0, and at R is equal to capital R, there is a surface, and we have Q is equal to H into T surface minus T A. If you are doing a forced air cooling, on the other hand, if it is a quenching operation, a similar kind of a boundary condition can be applied, but in this particular case we will use a different heat transfer coefficient only. Okay? So the intensity of the cooling will depend on the heat transfer coefficient. In this particular case, as I said, if you use normal air cooling will give you a value of H, suppose if it is 1 unit. Forced air cooling may give you an H which is of 3 or 5 unit. On the other hand, if you use it quenching operation, in that case this H could be 1 or 2 order of magnitude larger. That is what the intensity of cooling determines, the severity of cooling determines the heat transfer rate, and so therefore, a forced convection boundary condition, this basically implies that how intense. When you quench it, there is going to be huge amount of stirring taking place, in the vicinity of the solid surface, because you have bubbles formation, etc. Boiling is taking place. On the other hand, if you have forced convection, air passing over the sample, in that case, what happens is we have significantly more heat transfer coefficient than it is in this case of normal air cooling, etc. So, the heat transfer coefficient is to be given to us. Okay. Once we find out the heat transfer coefficient, this also I have told you that heat transfer coefficient comes from forced convective correlations, okay, forced convective heat transfer correlations. So, you should be able to pick up the right kind of a forced convective correlation, and then from that, based on the velocity of the air, the properties of the fluid, etc., you should be able to compute this H, and this T ambient could be the ambient temperature, which is the room temperature, as it is in the case of this, and therefore, all the boundary conditions will be known. You should be able to solve these equations in order to find out that where how is the temperature changing as a function of time during the cooling process, where you have been able to form fine perlite, and wherever you are forming coarse perlite, you can compare, because the rate of cooling at this particular point, the surface cooling rate and the center cooling rate are not going to be same, okay, because of the thermal resistances. So, there is going to be different in the structure itself, and this is going to be more valid if you try to look at the quenching problem. For example, the surface may exhibit a rate which is greater than the cooling rate, because you have plunged the solid sample, hot solid sample, into water. So, therefore, the surface may exhibit. On the other hand, the center may exhibit this or this, depending on the size of the rod. If the rod has a huge diameter, there is a great possibility that the rate is going to be smaller than the critical cooling rate. So, if you take a sample like this, the wire cross section like this, rod cross section like this, in that case you can say that, well, the surface is critical cooling rate greater than. So, you can find out that which are the points which gives you, and then you can say that by knowing the temperature from that equation for every hour, I will be able to know that how the temperature varies. So, the cooling rate will be known here. The moment I fix the R, I have only temperature as a function of time. So, at this point I will be able to know the cooling rate, and what I am saying, at this point, at this point, at this point, or all the start points, I find out that my rate of cooling is greater than the critical cooling rate. Elsewhere it is not so. Okay? So, therefore, I can say that this represents a section where the critical cooling rate, or the rate of cooling is less than the critical cooling rate. So, therefore, one should be able to find out that what is the region close to the center. We always know that you never get retained austenite here. It is the core of the rod or core of the object where you can get retained austenite, because of the simple fact that at the core the rate of solidification, rate of transformation, or the rate of cooling is going to be significantly smaller than the rate of cooling at the surface itself. So, by using this, the governing equation of heat transfer, by using appropriate boundary condition in conjunction with auxiliary equations like, or auxiliary information via on the basis of iron carbon phase diagram or time temperature transformation diagram, one should be able to address the formation of fine perlite, as in the case of air cooling operation of a rod, or one should be able to find out that what is the volume of the retained austenite which is there in the system or in the wire cross section, and in that case one will require that clubbing of the heat transfer theory with the relevant kinetic informations. So, the time temperature transformation diagram, if it is provided to us for that grade of steel, in that case this can be synthesized with the heat transfer, and the combined framework can be developed to predict that within the wire where can we get retained austenite, or retained austenite is at all forming or not. And here also you see that lot of the entire thing, this the microstructure, the development of the various phases, they are basically related with the theory of the heat transfer. There is conduction phenomena which is involved in this particular case within the solid. Outside the solid we have convection, or maybe a more complicated scenario like boiling heat transfer. Yesterday we talked about the combustion, the furnace heating operation, and as I said, in the furnace itself, how is the heat being generated? The heat is being generated because of combustion of the fuel. That is again another subject, combustion heat transfer, okay, where we have different gas mixing or liquid gas mixing, and then as a result of which combustion takes place, heat is being generated. That is altogether a different subject we have not studied. So combustion heat transfer, boiling heat transfer, the advanced topics of heat transfer would be integrated. Okay, we only know that conduction, convection, and radiation, but as far as we are concerned, we see that the effect of the boiling heat transfer, if it is at all there, this is going to be accommodated by the heat transfer coefficient. So we have to know the appropriate. But the temperature profile within the solid will be governed by this governing equation, which subject to the boundary condition. If the boundary conditions are specified, can be solved. If it is integrated with the iron carbon phase diagram or time temperature transformation diagram, then lot of things beyond temperature calculation can be attempted. The next topic I want to do is the melting of, which is also a very similar kind of an operation, but there is a phase change now involved. So it's a little bit complex. This is very common in metallurgical or industries or in materials processing problems, particularly in the fabrication. In the making of steel, in the making of alloys, we often encounter melting, and melting basically, if you take a liquid metal here, you can take melting can be involved in polymers also. For example, polymers also undergo melting. There are everything some are low melting point constituents, some are high melting point constituents. Okay, so metals which are basically, for example, if you consider a metal which is at a temperature greater than its melting point, so it's in the liquid phase, and in that liquid, if you add a solid material, and that solid material undergoes, basically, if we want to change the composition of the liquid, okay, we want to produce a mixture of two different solids. So that is the whole objective of or the same material itself. I may have a liquid of the same material, and then I can add, to increase the more volume, a same kind of a material. For example, in steel making, in aluminum making, you have heard about the dissolution of the scrap, for example, melting of the scrap. Okay, so steel scraps are being added into the steel furnace. So we have a molten steel, okay, and then into that we add steel in order to increase the volume. Electric arc furnace, for example, we know that the scraps are being melted there. So initially some scrap melt, then the scrap melts and creates a liquid, and in that liquid additional scrap melts. So melting is a very common phenomena in metallurgical industries, where we deal with solidification. Of course, is the reverse of melting, which is also very commonly encountered because we supply molten material not in liquid state but in solid state. So in those industries where we produce metal, invariably a solidification process is involved. So we consider a problem. So melting, we take a simple case to demonstrate that what sort of a heat transfer fundamentals are involved. So melting of a metal in another metal. Okay. So this metal, melting of a metal which is solid in another metal which is basically liquid. That's the problem. So it can be, we can have a steel here, and this could be aluminum here or copper here. Now, whether after melting they form a homogeneous phase or not, that is not the subject here. Okay? That is a different issue altogether, but we want to say that this is solid, heat is being transferred from the liquid to the solid, and as a result of which the solid melts. Obviously, we understand that the melting point of the solid is less than the melting point, that then only the melting will take place. Okay. So, liquid is at a higher temperature. So, this is, as you can see, steel could be at 1600 degree centigrade, and aluminum melts at about 780 degree centigrade or so. That is what it is. In the other case also, for example, that we will study later on, melting does not take place, but dissolution takes place when this condition is not satisfied, or the reverse happens. For example, if you add carbon into steel, carbon does not melt in steel, okay? But carbon has great solubility in steel, so carbon dissolves in steel, just like the way sugar does not melt in common water, sugar dissolves in molten water, water. So, because the melting point of sugar is larger than the room temperature in which the sugar is put. So, we will talk that when we talk about mass transfer, the dissolution process, but for the time being let us talk about the melting operation itself. Now, the melting basically results that we have a solid transfer of heat from the melt to the surface, and and if this heat which is transferred to the surface is sufficiently large such that the surface can attain a temperature greater than 780, in that case that point will be liquid. Now, I have shown it to be a spherical geometry for the sake of convenience. If you understand it for spherical geometry, we will understand it for other geometry. If the geometry is often irregular, in that case an equivalent surface area is typically determined, as you all know. Okay? So, if you take volume, okay, and then you take mass, the surface area, and then you can find out a characteristic length scale. So, equivalent surface area for non-spherical geometry or irregular geometry, but it is sphere, so it is very simple geometry. Now, surface area, perimeter, etc., everything is going to be known, and I have deliberately considered it so that the problem becomes simple. Now, the heat arrives from the liquid at the surface, heat also gets through conduction into the solid. So, if you look at the equation again, this is a sphere, so we have basically theta and phi symmetry here. And the temperature within the solid is a function of radius and time. That is what we expect. So, if we look at within the solid, that I want to find out that how is the distribution. So, we are not looking outside the surface, we are looking from the surface inside, and then this becomes a pure conduction problem. Okay? And then it is an unsteady state conduction, because this is a solid sphere which is being projected at t is equal to 0. So, initially this solid is at room temperature, then all on a sudden it is plunged into the liquid melt, which is maintained at a constant temperature, and suppose this remains constant, and then as a function of time we know that because it is 780, it is 1600, it is going to be in liquid phase. I want to find out, for example, that what should be the complete melting time of this particular solid. And if you look at the process, it appears that temperature is going to be a function of the radial coordinate and time, and wherever the temperature touches 780, and then the solid will turn into a liquid. And in this particular case, we also know that there is going to be a phase transformation, and that phase transformation which will take place at the surface is the solid to liquid phase transformation. And this has significantly larger delta H value. of megajoules per kg. That is the kind of value we are talking about, the latent heat of solidification or melting in this case. So, within the solid, for R which is greater than 0 and which is less than is equal to R sub 0. R sub 0 represents the solid, okay, initial radius of the solid. Now, the radius of the solid, and this radius, as we all know, is a function of time. So, therefore, the radius of the sphere is changing as a function of time. This brings in a, so it is a different problem than the last two problems that I have discussed, because there is a change in the domain of conduction heat flow. So, that is what I said, that for R greater than 0 means that from the center to the surface, and this R represents the radius of the sphere, not the initial radius, but the radius of the sphere, which is an instantaneous radius of the sphere. So, within this, the governing equation is that is what it is. So, within this solid, that is the governing equation. Now, if you look at this at time t is equal to 0, as I said that the sphere is at room temperature for all values. So, R greater than 0 and R 0, where R 0 represents my initial radius of the sphere, and that is constant. So, therefore, temperature is equal to T sub 0, which may be say room temperature. And then at R is equal to 0, so T greater than 0, the initial condition R is equal to 0, I have the standard boundary condition because of symmetry, and at R is equal to, I cannot write the boundary condition at R is equal to R 0, because R 0 is not fixed, itself is changing. The radius of the sphere is changing as a function of time, but no matter whatever is the radius, okay, at that surface value, this represents an instantaneous surface of the sphere or instantaneous solid liquid interface, and I can say that at that particular point, okay, we can have two conditions can be applied, that this represents the heat transfer coefficient, where I have T liquid minus T melting aluminum. That is, or one can also say the other kind of boundary condition could be T is equal to T melting point, because the surface has always attained a melting temperature. Okay. Now, if you look at this equation, then what happens is that I have one equation and one unknown. The temperature needs to be calculated because rho, Cp and K are values are known, okay? But the entire formulation that I have shown here has brought in an information that this R itself is not known, because this is a function of time. I only know the value at t is equal to 0, this R becomes equal to R 0, but t is equal to 0, the solution is known. I want to find out the solution at t is equal to 0 plus delta t, and that 0 plus delta t, this R itself is not known. The information on R comes out from a surface heat balance, which is like k dt dr if you say heat transfer coefficient, okay, Ts, this is the rate at which the heat transfer coefficient TL minus T. And that is equal to this essentially tells us this is an additional heat balance equation at the surface. Okay? So, if you take at the surface, the heat from here, if you take a little which is going through conduction, the heat which is coming by convection, and the two together must balance the latent heat which is evolved in the whole process. Okay? So, this is a local heat balance equation, and this, if you see that now I have two equations, these are all known. This is known, this is known. These solid fractions can be calculated once we know that how much is, wherever it is more than, if T is greater than Tmp, then we have gamma s is equal to 0, gamma L is equal to 1. So, the solid fractions, once the temperature is known, which we will be knowing that whether it is in the solid or the liquid phase. So, the rate of change of melting, or this is actually the rate of melting, the change of the solid fractions as a function of time. So, the rate of melting can be known once the temperature is known, but what happens when you club this equation with this equation, then you have prepared a framework where you have two equations and two unknowns. Now, suppose you make an approximation that the solid has a large thermal conductivity. A large thermal conductivity means, I have already also told you that we have a number called Bio number. So, there we can see that we will have negligible temperature gradient, because the thermal conductivity is large. So, as a result of which temperature is going to be flat or uniform. So, the gradient of temperature is going to be equal to 0, and in that case, therefore, within the solid the temperature is not going to be changing. So, this term can be taken to be is equal to approximately is equal to 0. So, for large thermal conductivity, the gradient of temperature within the solid will vanish, and therefore, since heat transfer coefficient is known, you should be able to find out. This is actually, I have written it wrong, I think this should be written as rho h. Okay, that's fine. So, once you do this, you should be able to find out the solid fraction as a function of time on the basis of this equation itself, because this is known, this is known, this is known, this is known, and this parameter, the solid fraction itself, is going to be, I can also convert this equation in terms of the rate of change of, simply by material balance, this how much has, because I know the sphere, so how much has liquefied, and as a result of which how much radius has changed. These are related parameters actually. So, this term can be formulated in terms of the rate of change of the radius also, because the rate of change of solid fractions is related to the rate of change of the radius of the material. So, therefore, on the basis of this, I should be able to find out that at what rate the radius of the sphere is changing. When I assume this case that the solid has very large thermal conductivity, there is negligible thermal gradient. So, in that case, one can say that, look, I do not really have to solve this equation, because what does this equation gives me? This equation gives me that how temperature as a function of R and T. But that I am assuming thermal conductivity to be large. So, I am no more concerned with, so it is a case of lump parameter scenario, and in that particular case, this simple equation will tell you that at what rate the solid fraction is changing, or at what rate the radius is changing, and as a result of which you should be able to find out that, well, at time t is equal to 0, this is the scenario. At time t is equal to some time, this is the scenario. At t is equal to some time, at t is equal to some. That is how simplify this equation. But if this is not true, in that case, what happens is, you will club the equations together, and clubbing the equations together, you have to develop a framework that you have two equations and two unknowns. Okay? And these two unknowns are, one is the temperature field itself, and one is the radius of the solid object, and this is called a moving boundary problem. The domain is not fixed as a function of time. The domain in which you are calculating the temperature field itself is changing as a function of time. Okay? So, I will continue with this. I will give you, if you cannot correlate the two, I will write down the expression in the next class and then show you that how this term becomes. So, the moment you put this term here, in that case what happens, you can visualize it that it is actual unknowns are radius as well as the temperature. There are two unknowns in the whole thing, and if you write it like this, you have only one condition will be necessary, that for example, if you look at it this particular form, then you require only one condition, that at t is equal to 0, what is the value of gamma s? The gamma s value is equal to 1 solid fraction, and you will say if you write it in terms of partial with respect to r, and you will say at time t is equal to 0, what is the value of r? That is equal to r0, and that will constitute the initial condition for this equation. So, I have two equations, the boundary conditions are known, I can solve these equations, and I can get not only the temperature field within the solid, but also I can find out that what is the instantaneous RT, and that will allow me to find out that how does the radius changes as a function of time, and at what point I attain a value of almost practically 0 radius, which tells me that this time actually represents the complete melting time of the alloy. We will continue this.